Within this short video, Peter, Eldred, Kira Lee and myself will be discussing the mathematical modelling of zombies with research conducted by Robert Smith, ? And that isn't a typo, that is actually his name. In today's modern world of pop culture, one fantasy monster has stood out as a constant fear for a possible future, the rising of the living dead. Now, the idea of the deceased rising from the dead and trying to kill off the living may just seem like a good TV idea, but this idea isn't restricted to fiction. In our world, there are a number of parasites that infects the host and ultimately controls it. One well-known example is cordyceps, a fungus that infects ants and alters their behaviour. These infected ants distribute fungus spores as widely as possible to other ants, before ultimately killing its host and infecting many others. Sounds pretty familiar to how one might imagine a zombie apocalypse from starting. Now, this concept of a zombie apocalypse has fascinated the world for years, and studies conducted by Cornell researchers using the same research concepts for both the Ebola and measles found that it would take less than 100 days for the United States to be completely overrun by zombies. Physicians from the University of Leicester further support this research, stating that within the initial 100 days, not only would the United States be overrun, the entire Earth would be left with less than 300 humans.
Define a zombie as being both living and dead humans capable of becoming zombies through infection. Human and zombies are capable of being killed. Using this generic zombie, we can define classes and parameters for the zombie outbreak. Classes include living humans, reanimated humans, and killed humans and zombies, respectively classified as susceptible, zombie, and removed. Parameters dictating how an entity changes classes include a susceptible dying naturally, a susceptible being infected, a removed infected postmortemly, or a zombie being killed, respectively called delta, beta, zeta, and alpha. Human birth rate is defined by pi. A doomsday scenario occurs if the number of susceptible humans does not stabilize above zero over time. Assuming an outbreak over a short time period, human birth rates can be ignored. Because zombies both cause and are created through human death, an increase in zombies leads to an increasing zombie birth rate. Thus, in the basic model, a doomsday scenario will occur if the zombies are not dealt with quickly.
The number of susceptible humans is determined by the birth rate subtracted by how many humans that are killed by zombies and how many that die of non-zombie means. The number of zombies is determined by the amount of people turned into zombies added to the removed that are added to the zombie class, subtracted by how many zombies that are killed by humans. The number of removed is determined by how many humans that die of non-zombie means added to the zombies killed, subtracted by how many removed that turns into zombies. To make the model more realistic, Smith adds a class, the infected, and a new parameter, rho, which represents the rate at which an infected turns into a zombie. This model is called the SIZR model. The new infected class is determined by how many susceptible humans are infected by a zombie, subtracted by the amount of infected turned into zombies, and how many infected that dies of non-zombie means. The zombie and removed class are adjusted to fit the new model. This model is closer to reality, but all humans still eventually die. A model with treatment would give some hope for the human race. A zombie who has received treatment would be moved back to the susceptible class. A new parameter C represents the rate of cured zombies. The susceptible class adds the component of cured zombies, while the same component is subtracted from the zombie class. This change makes a vital difference. It gives the susceptible humans a chance to survive, even if it is in small numbers. Still, the number would be above zero, which is a vast improvement from the previous models presented by Smith.
Figure 10 depicts what would happen should a plan to eradicate zombies with impulsive attacks occur. The figure shows a significant decrease in zombie population, followed by steep growth, and eventually 100% eradication of zombies. Applying mathematics to the real-world problems, not all mathematical options are viable. Figure 10 assumes that available resources can be mustered in time for a zombie outbreak and that everyone is prepared to fight. All assumptions mean that whilst the most effective, figure 10 is also the least viable option. This is why Smith concluded that a cure would be the most viable option with human survival. Smith uses both linear and population modelling to predict the likely outcomes of a zombie outbreak. Although zombies are at this point fictitious, There are many infectious diseases that could be modelled through this same mathematical process. The process of applying mathematics to a real-world scenario begins by clearly identifying the parameters, forming a basic model, and then using this basic model to test hypotheses determine the best course of action. These processes are similar to those taught in mathematical problem solvings in the classrooms today. Whilst this particular scenario is fictional, the mathematical processes involved can be applied to solve real-world problems.